Good afternoon, good evening, and good morning. Hello, everyone. My name is Karthik. I'm very excited to present this work from the University of North Carolina at Chapel Hill. Healthcare is an intrinsically complex field, and the increasing complexity and difficulty of tasks impose varying levels of cognitive workload, which affects healthcare professionals' performance. Suboptimal cognitive workload of healthcare professionals has consistently been associated with inferior task performance and a higher likelihood of medical errors. The National Aeronautics and Space Administration Task Load Index, NASA TLX, is the most widely used subjective measure of cognitive workload of individuals operating in high risk and time sensitive industries. The classical approach involves measuring all dimensions of NASA TLX, while recent studies suggest that only 4 dimensions of NASA TLX are adequate to measure the overall cognitive workload. Cognitive workload is a multidimensional and complex construct that is often affected by several nonlinear factors. Theory-driven and deductive approaches have been utilized in the past to aggregate these factors to define overall cognitive workload and build robust models for predicting objective performance. In recent times, inductive data-driven methodologies such as supervised machine learning classifiers have been applied to predict objective performance from perceived cognitive workload data. However, to the best of our knowledge, no previous study has utilized this methodology to predict objective performance of healthcare professionals using perceived cognitive workload data. The dataset for this study has been drawn from our previously published studies of healthcare professionals. These are grant-funded studies. The dataset contains 318 instances from 84 healthcare professionals performing tasks of varying difficulty, context, and requiring different human modalities for processing information in a simulated environment. The participants of each task filled out the NASA TLX questionnaire, and objective performance was measured at the end of the task. We used the cross-industry standard process for data mining, CRISP-DM methodology, one of the most widely used analytics models to implement the machine learning cognitive workload models. The process involves 6 stages, starting with identifying goals, understanding data, preparing data, model training, model testing, and deploying the model. The study aims to compare the classical and novel models in predicting healthcare professionals' objective performance by evaluating the classifiers on accuracy and capacity statistic. The classical model utilizes all the 6 dimensions of NASA TLX, while the novel models utilize 4 or 5 dimensions of NASA TLX. The data involved in creation of the classic and novel cognitive models include different combinations of NASA TLX dimensions. Data exploration is the first part of CRISP-DM, in which an analytic base table is built for discovering the nature of data and investigating its characteristics. The objective performance was categorized for each study into low, less than or equivalent to quartile 1, moderate, greater than Q1 and less than Q2, and high, which is greater than Q3. So thus all the classes in the objective performance were based on the quartiles. The main aim of this stage is to construct the final dataset for subsequent modeling. Here the dataset is divided into 2 segments, features and outcome variables, which is objective performance for the following cognitive workload models. The classical model involves all the 6 dimensions of NASA TLX's features. Novel model 1 uses only 4 dimensions, while novel model 2 and 3 use 5 dimensions of NASA TLX. In machine learning, the class imbalance impacts the creation of robust models as it tends to favor predicting the majority class or the minority class. In the current dataset, there are 2 minority classes, medium and high, and 1 majority class, which is low. To solve this issue, we used Synthetic minority oversampling technique, a widely used oversampling method to balance the target classes. Studies suggest that there are more than 85 SMOT variants, but for this study, we used the most widely used SMOT variants: equal resampling, minority resampling, and density-based SMOT. The number of instances in each objective performance class, as well as the total number of instances in the original dataset and the training dataset with or without SMOT variants is shown on this table. The number of instances with SMOT variants is higher than the original dataset and the training dataset without SMOT. The aim of this stage is to develop computational models by learning from data. We surveyed the main classifiers and selected the following 5 classification techniques to tackle the cognitive workload problem from different perspectives. For instance, we used the k nearest neighbors for similarity based, random forest for information based, and to assess for errors, we used the NU support vector machine, and the Bernoulli's Navy Bayes was probability based. To develop robust predictive models with a higher degree of generalizability, cross-validation can be used for model training. A randomized stratified split was conducted on the original dataset, with 80% going for the training set and 20% for testing. The stratification was done to ensure that the class imbalance was retained for training and testing. The training dataset was then oversampled with multiple SMOT variants, and subsequently we used a tenfold cross-validation, a widely used method for small datasets. In this study, after cross-validation, the models were tested on the held out test set, that is the 20% of the instances. Now, in this stage, the aim was to test the classifiers from the earlier stage, evaluating them on their inferential capacity and accuracy. Overall, 84 final classifiers were built, 4 cognitive models multiplied by 4 classifiers, and 4 with and without SMOT. We selected 2 metrics, prediction accuracy and kappa statistic, to evaluate the final classifiers. Accuracy helps in the overall interpretation of a classifier, while the kappa statistic compares observed accuracy with expected accuracy and accounts for random chance. The kappa statistic because it accounts for random chance, is less likely to be misleading. Thus, combining kappa statistic with accuracy provides a more in-depth interpretation than using accuracy scores alone. Now, in terms of the results, the highest cross-validation accuracy for predicting objective performance is achieved by the classical model. Followed by novel model 2, 3, and 1. Now, in terms of equal sampling, in terms of the cross-validation accuracies grouped by with and without SMOT variants, interestingly, it was the equal sampling method that had higher accuracy than other SMOT variants and the without SMOT. Now, in terms of the accuracy of the classifiers, random forest and the NU-SVM were the two classifiers that achieved higher accuracy in comparison with other machine learning classifiers. Now, as observed in the model testing phase, the classical model continues to have the highest accuracy in predicting objective performance than the novel models. However, when we observe the cross-validation accuracies grouped by with and without SMOT, interestingly, it is without SMOT that is higher than those with SMOT. And in that regard, there is differences between the testing and the training phase. But The NUSVM and RFC are the most robust machine learning classifiers to build the cognitive workload models in this data set. So in that way, that in here, in terms of the machine learning classifiers, we find identical machine learning classifiers scoring high accuracy both in the test and the training set. What we then did was we tried to look for the density plots. The density plots of testing accuracies also confirm that the classical model, which you can see here, is more compact and has taller curves on average, and is thus superior to the novel models. Further, the distribution of the distribution of the kappa statistic also shows that the classical model is more reliable in predicting objective performance than the novel models. Thus, clearly based on the testing accuracies and kappa statistic, the classical model has consistently outperformed the novel models. This study utilizes a data-driven machine learning methodology to suggest that all 6 dimensions of NASA TLX may be used to better predict healthcare professionals' objective performance than the novel models that utilize only 4 to 5 dimensions of NASA TLX. Overall, our findings are consistent with Mustafa et al. Study that used non-healthcare data to develop data-driven computational models of cognitive workload to predict objective performance. Important differences between the present study and their study with that they considered 2 subjective measures of cognitive workload, NASA TLX and workload profile. And within NASA TLX, they used raw scores of all dimensions and the weights of all dimensions and the total TLX scores as independent features. However, in this study, we compared only the raw scores of 6 dimensions of NASA TLX with 4 and 5 dimensions of NASA TLX to predict healthcare professionals' objective performance. Further, we use multiple smooth oversampling techniques on the data, while Mustafa et al. Used only dB smooth for oversampling. The study, however, has several limitations. Our results are based on a small data set of healthcare professionals, of which 62% are radiation therapists, at a single large academic medical center drawn from 3 Agency for Healthcare Research and Quality grants. The objective performance in each of the study is assessed differently, and hence findings from this study, although promising, cannot be generalized. Further, we only used raw scores of NASA TLX dimensions as independent features, which limits the generalizability of study findings. Future studies, we believe, should involve bigger data sets and also compare the classic cognitive workload and novel cognitive model in different healthcare professionals, for example, clinicians versus non-clinicians, and examine if there are significant differences between the classical and the novel cognitive workload models. We thank you for your patience, and before we end, we would like to thank Professor Arcot Rajashekar, who helped us in assisting in the study conception. Thank you so much.